Let's say your unknown didn't contain silver ion or lead. If your unknown didn't contain silver or lead and you add HCl, what's going to happen? No PPT is going to form. And so after you start adding some HCl, you'll begin to notice no PPT is going to form. Are you going at that point, are you going to add all of the HCl? You probably shouldn't, because if no PPT is forming and the purpose of the HCl is to form the PPT, then it's probably best not to overdo it with the HCl. And so what that means is that if you get no PPT, then the next step is to filter, but you have nothing to filter. And so every semester somebody comes up and asks me what I should do. You know, I didn't get any precipitate. What should I do? Should I filter it? And then what do you think? Should I filter it? Yeah, there's nothing to filter. If you're filtering, you're trying to remove precipitate, but if there's no precipitate, there's no purpose in filtering. In fact, all you have is what we call filtrate, and if you only have filtrate, then we just continue on this branch. And so the situation with the lab procedure is written like this cookbook style, but you can't cookbook the unknown. That's because the unknown doesn't contain everything. So what we have to do is, it's easier to just go off the flow chart. If we don't get a precipitate, we're going to jump to this branch, rather than looking at the procedure itself in the lab manual. And the procedure in the lab manual says, okay, the next step is to filter this. Next step is to wash the precipitate. And so just be aware of that. And so another scenario is, what if you had lead? Well, if you had lead, then you get a white precipitate, but when you heat it up, that white precipitate completely disappears. And so some people say, well, if the white precipitate completely disappears, can you filter that? No, but the problem is when lead cools down, then it reprecipitates, and then they can precipitate that. And they reprecipitate the lead, but it's not silver, and they add the sodium hydroxide and it doesn't turn black. And they come up to me and they go, oh, mine didn't turn black. You know, it didn't turn black because, well, you probably filtered out lead. Probably got cool and you filtered out lead. Except I'm not going to tell you that. I'm going to ask you to try to figure it out, what happened. You know, but it happens all the time that students will get very confused because they're trying to follow along on the procedure, but it doesn't follow the procedure exactly. Okay, so we continue down here. If you have silver, great. You're going to go through and then you're going to test the precipitate with sodium hydroxide. It's going to turn black. Then we're over on this branch here. And in this branch, what is the purpose of adding the Ki? Ki? Yeah. To get a yellow PPT. That's the purpose of adding the Ki. If we get a yellow PPT, then we can separate. If we don't get a yellow PPT, then we continue down here. The purpose of adding the sodium hydrogen sulfate or sodium bisulfate is to get a white PPT. And so if we get a white PPT here that's positive for barium ions, if we get a yellow PPT here that's a positive for lead ions. We might not get any of those PPTs. We might end up at this branch. Let's say you didn't have any silver, you didn't have any lead, you didn't have any barium, you didn't have any manganese. By the time you hit the end, or actually, let's say we have manganese. If we have manganese, boy, you're going to have a lot of solution here. You know, your test tube might be overflowing because you poured in so much stuff and nothing's really happened. And so if that's the case, then switch from test tube to beaker. You know, try that instead. But the problem also is solution dilution. You know, when the solution gets too dilute, it's really hard to detect some of these. Especially things like a gelatinous precipitate. Sometimes the gelatinous precipitate, when it's very dilute, is hard to isolate. And so if it's looking bad, by the time you reach here, one option is to boil off some of the water, you know, to make it more concentrated. You just heat it up and just boil off the water. Get the solution volume down, but that's the last case scenario. Hopefully this works here when you get this precipitate, and then you can dissolve it, the precipitate using some nitric acid, and then oxidize using sodium bismutate. That would be good. All right, so we're going to go through the procedures. Your known is not going to be, well, it's going to be different than your unknown in one way. You had two separate known solutions. You had the cation known solution that you got from the stockroom, and you have the anion known solution that you get from the back. The unknown is going to contain both cation and anion, and so they're going to give you a lot of it. They're going to give you a lot of it because you have to use 12 milliliters for this test, and then you have to use 3 milliliters for the individual tests, okay? And then you might have to repeat. And so this is what. So we're still on 12. Yeah, we're going to finish up. Actually, it's just kind of a repeat of what we already did. Yeah, essentially you do it all over again, but it's not going to be the same. It's going to be different. Since it's
what do we do? What do we do with the results from last time?
Yeah, question about the lab report. What do you want us to do?
okay. Let me talk about the lab report right now. The lab report's going to be pretty well. Lab report is going to be either pretty easy or pretty difficult. We're not going to do this. We're not going to fill in the report sheet here. You can leave this blank. This is what I want for the lab report. It's going to be quite a bit different than what they're asking for here. And so the first one is the unknown. And so this is for the report. You know, we just need the unknown number, whatever. And I just want to know what cations you found. So say, for example, I found silver, so I'm going to write silver ions. No. If there was no silver, then write whatever you found. It could be silver ions, etc., however many you found. And so, I don't know. And so you're going to just list the cations that you found, and then list the anions that you found in your unknown. That's it.
Just like a cute little piece of paper with that on it?
Yeah, except now there's going to be the next part of this. What are we going to do for the known? The known had everything in it. The unknown just had some stuff in it, not everything. And so for the known, I want you to do a little more. And so this is what I want you to do for the known. The known, we'll start off here. And the first tests are going to be for silver, lead, barium, and manganese. So we got silver, lead, barium, and manganese. And so what you're going to do is you're going to write out all the chemical reactions that occurred in this, including the no reactions. And so the first step here is we're adding HCl. So silver ions plus HCl, what happens here? Well, we get a precipitate of silver chloride, solid. Lead ions plus HCl, what do we get? We get a precipitate of lead 2 chloride, solid. Barium ions plus HCl. Well, is barium chloride a precipitate? No. Chlorides, bromides, and iodides are all soluble, except for silver, lead, and mercury. Well, we don't have any mercury. Everything else is soluble. And so these are going to give no reaction because we're not going from a stronger acid to weaker acid or anything like that. And so those both are no reaction here. Okay, in the next step, we heat this. So when we heat silver chloride in water, mixed with water, nothing happens pretty much. It stays a precipitate. However, when we heat the lead, then something happens. We heat the lead and then the lead dissolves. So we'll get PbCl2 aqueous. So that dissolves that. And so we've isolated the silver chloride. Once we isolate the silver chloride, then we're going to add some sodium hydroxide to that. And that should form some silver hydroxide solid. But silver hydroxide solid is not so stable, so that silver hydroxide solid actually will decompose. Let me write that up here like this. 2 silver hydroxide solids decompose into 1 silver oxide solid plus an H2O liquid. And so these are all the reactions that are happening here on this side. So this is the test for silver, pretty much. Okay, let's move on to the test for lead. And so you'll just write this on the, let's say, loose leaf paper or sheet of paper or something. Okay, now as we go for the test for lead, we have PbCl2 aqueous. PbCl2 aqueous, it's a strong electrolyte, so it's going to form Pb2 plus 2 chlorides here in solution. And so what we're going to have is we're going to have lead ions, barium ion, and manganese ion in solution. And then what are we adding to it? Ki. And so lead likes iodide, so we'll need 2 iodides for that, and it's going to precipitate out PbI2. Chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury. Barium iodide is soluble. That's not going to precipitate out, so we get no reaction. Manganese 2 iodide is soluble, and so we get no reaction there. And so this is our yellow precipitate of lead 2 iodide. And so we separate, you know, the barium and manganese, there's no reaction, and so we're here now. And so the next thing we're going to test for is barium. And so when we go on to test for barium, our solution is going to contain barium and manganese. And then what are we adding to it?
That's not HSO4. That's sulfuric.
HSO4 is called what?
That's sulfuric acid.
No, H2SO4 is sulfuric acid.
That's
HSO4 is called
sulfate.
bisulfate, sodium bisulfate, or sodium hydrogen sulfate. Well, barium, well, what about sulfates? Just sulfates in general. Sulfates are all soluble except for, silver, lead, mercury, calcium, strontium, barium. And so barium sulfate is insoluble. So what's going to happen is barium ions are going to knock the hydrogen off that sulfate. And so we're going to precipitate out barium sulfate, and the sodium ions are already knocked off, but the hydrogens get knocked off by the barium ions. Manganese sulfate is soluble, and so there's no reaction here. We're not forming a gas, we're not going from a stronger acid to weaker acid. There's just no reaction. So that's for barium there. Okay, once we get rid of the barium, then all we're left with is manganese. So let's take a look at that next here. So what are the reactions here? Well, the first reaction is we're going to mix it with hydroxide. Well, manganese likes hydroxide. This is kind of a composite between net ionic, and complete equation. Sodium hydroxide really is sodium ions and hydroxide ions, but I'm leaving it as sodium hydroxide just because that's the reagent we're adding. This is sodium salts. All sodium salts are strong electrolytes. And so this is going to form manganese 2 hydroxide, which is the light brown precipitate here. to this light brown precipitate, in the next step, we're going to add nitric acid. 2 of those. And so this is going to form what? Manganese nitrate, manganese 2 nitrate, and water, 2 waters. So this is going from stronger acid to weaker acid. So driving force. This is not a precipitate. This is aqueous. And so stronger acid to weaker acid. Well, manganese 2 nitrate consists of manganese ions and nitrate ions. It's a strong electrolyte, so it should be broken apart. Okay, the next thing we're going to add is this. What was this called again?
What's BI?
Yeah. BI is bismuth. What's it called?
So that's sodium and bismuth with
Sodium bismutate.
bismuth.
It's located in that hood over there. You haven't gotten to it. The reason I kept it in the hood over there is so that, yeah, so you don't accidentally breathe it in. You know, because it turns out that, what do you think is a stronger oxidizer? Chlorine or sodium bismutate? Sodium bismutate is a much stronger oxidizer. And what did that guy die from at Wild Wings? Buffalo Wild Wings. From chlorine.
Chlorine gas.
And sodium bismutate is even, I don't want anybody dying in this class. And so, yeah, and you know, some people, no matter how hard they try, because some people will generate a huge dust cloud of sodium bismutate and be trying to be inhaling it for some reason, you know. So if there's a dust cloud, hopefully it gets sucked into the hood there. Doesn't poison you. Uh-huh.
The last lab that we turned in, that's what's on the screen right now.
Yep.
So we still not finished with that lab.
Which
Should
one?
have turned it in.
Did you turn it in?
Yes, I'll get off of this.
Oh, no, experiment 10 is done. We're not an experiment. Were you here last week, Neil? Yeah, that's what I thought. We're doing the same experiment we did last week, which is experiment, I don't know, this is my book, it's experiment 12.
Well, here's 11.
It's 11? Okay, we're on experiment 11.
You turned that in, didn't you?
No, you can't turn it in yet because,
Well, I turned it in.
yo, you turned it in? All right. All right, you should take it back then.
Okay.
Yeah, because there's 2 parts to this. The first part's the known, the second part's the unknown. And so why do we need such a powerful oxidizer? This stuff is fine if you just don't, you know, if you're just careful with it.
Need it to slash it in. Take some electrons.
Yeah, well, we need it to take some electrons from manganese. And so what we're going to do is we're going to oxidize manganese. In fact, we're going to try to oxidize it all the way to
Emmons.
permanganate. Permanganate itself is a strong oxidizer. And so permanganate is actually a very powerful oxidizer. And so we're going from an oxidizer to a powerful oxidizer. That means this oxidizer must be even more powerful. Otherwise, this reaction won't go. It will not be spontaneous. Permanganate is a better oxidizer than chlorine, yes. But, you know, they use permanganate to tan leathers and do that kind of stuff. But what's the reaction here? Okay, let's take a look at the reaction. We haven't hit the redox chapter yet. Well, we could derive this reaction, but we're just going to copy it down from our lab manual. Okay, so it looks like we have the 2 manganese 2 plus, 2 manganese 2 ions, plus 14 hydronium. I'm not going to use hydronium. What I'm going to do is I'm going to use hydrogen ion. So plus 14 H pluses, plus 5 sodium bismutate solids, plus 5 NaBiO3 solid, This is going to produce 2 permanganates. 2 permanganates plus 5 bismuth 3s plus, it says 21 H2O, but I cut down some of the H2Os because I'm not using hydronium, so I'm going to cut this down 14. So that's 14, 7 H2O plus 5 sodiums. Plus 5 sodium ions. All right, so this is our redox reaction. The manganese 2 plus is our reducing agent. The acid and the sodium bismutate, that's our oxidizing agent. That's going in the forward direction. Going in the reverse direction, permanganate is our oxidizing agent. And so this is a competition between these 2 oxidizers, sodium bismutate or permanganate. Which one's stronger? Sodium bismutate stronger, permanganate's weaker. So this driving force for this reaction. What's going to happen here is the bismuth is going to oxidize. The bismuth, do you know what the oxidation state of bismuth is here?
3.
Oxygen is -2. -2 times 6 is -6. Sodium's +1. So -6 plus 1 is -5. Bismuth must be +5. And so this is bismuth 5. Bismuth 5 is going to go to bismuth 3, so gains 2 electrons. Each bismuth gains 2 electrons. This is going to take them from manganese, because manganese goes from +2 to, what is manganese and permanganate? Manganese and permanganate's +7. So this is the reaction. It turns out that manganese 2 plus, this is light pink. Sometimes it's so hard to see the color. It looks like a CCS, clear colorless liquid or solution. But this doesn't. This is a light pink solution. This is a dark, permanganate's dark purple solution. Permanganate in water looks like grape juice. But don't drink it. Grape juice. And so when you see the solution go from a light pink or colorless to dark purple, then it's positive for manganese. All right, so that's manganese, and then we go to ammonium. Take a look at the ammonium test. This is going to be an individual test, so we're going to start with all the cations again. So for ammonium, these are the reactions that are occurring here. We have ammonium plus hydroxide, or sodium hydroxide. Leave it. So what happens here? Well, ammonium's an acid, hydroxide's a base, and so we're just going to transfer hydrogens. So we're going to form ammonia plus sodium ions plus water, H2O liquid. Ammonia is normally a gas, and it can evaporate off the surface. If ammonia evaporates off the surface, it will form ammonia gas, NH3 gas. And then we can test that with litmus. Blue litmus is for acids. Red litmus is for bases. And so what we're going to do is we're going to test this with red litmus. Okay, red litmus is for bases because red litmus is an acid. And we can write the formula for red litmus as HLIT. LIT because it's the formula for the litmus anion is kind of big. So this is just shorthand. So what's going to happen is we're going to have a hydrogen transfer, and so we'll form ammonium and LIT minus. LIT minus is blue litmus. And so we can use this acid-base reaction to convert from red litmus to blue litmus, and that would be a positive test. for the presence of a ammonia gas. Okay, like I said, your unknowns will contain the anions, and we'll have to test your unknown for anions. What anions are we testing? Well, the first one we'll test for is chloride. So if there's chloride present in your unknown, we could detect the presence of that using silver nitrate. Silver ions like chloride ions, and it'll precipitate out silver chloride solid. Nitrate over here. So again, this is kind of a composite. I really should split apart silver nitrate, but I'm not, because that's our reagent that we're using. And so silver chloride, this is going to be a white PBT. Oops. White PBT. I forgot to do something. Forgot to do a couple of things, sorry. Let me back up just a moment here. Well, let me just finish this one and then I'll back up. I want to back up because what happens with the other anions? So we have sulfate. Well, sulfate and silver nitrate should precipitate out silver sulfate. But the problem with this is it's fairly soluble. And so what we can do is at these concentrations, it won't precipitate out. So we aren't going to get a precipitate of silver sulfate. In fact, we're just going to get NR here. The silver sulfate's borderline. So maybe I should change the solubility rule not to include silver sulfate. And then we have nitrate. Nitrate plus silver nitrate yields no reaction. There are side reactions in the ammonia test, and so I need to talk about the side reactions here. So what else might be present? Well, we got ammonium. We also have silver. And so we have ammonium, we have silver, we have lead, we have barium, and we have manganese present. And so what happens if we add sodium hydroxide and we're trying to react the ammonium? What's going to happen is the sodium hydroxide can react with silver ion. So silver ions plus sodium hydroxide, this yields silver hydroxide, solid. This silver hydroxide, however, decomposes. And so if I take 2 silver hydroxides, I can make 1 silver oxide plus H2O liquid. And silver oxide is a black PPT. And so sodium hydroxide will just attack the ammonium, but sodium hydroxide also attacks silver ions. Sodium hydroxide also attacks lead. And so lead 2 is going to form PbOH2, which is a white precipitate. Lead 2 hydroxide is a white PPT. So what else does hydroxide attack? Well, hydroxide are all insoluble except for group 1, ammonium, and calcium, strontium, and barium. Well, barium hydroxide turns out to be soluble. So when we react it with sodium hydroxide, there's no precipitate. And so we get NR. But, you know, if it's not group 1, ammonium and calcium, strontium, barium, then it's going to react with hydroxide. So manganese is not, and so manganese should react with hydroxide. And it's going to form manganese 2 hydroxide solid. Manganese 2 hydroxide solid is with the light brown PPT. So it depends on what cations your unknown has, and that's going to dictate which of these side reactions, if any, occur. All right, so that was the ammonium, and then we're at chloride. And then we're going to jump to sulfate next. Sulfate's a little easier. And so what are the reactions that are happening with sulfate? All right, when we test for sulfate, then we want to add barium nitrate. Okay, if we add barium nitrate to a solution that contains sulfate, barium like sulfate, and so barium like sulfate, it precipitates. So we end up with a white precipitate here. How about chloride? Does barium like chloride? Well, chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury. Silver, lead, and mercury like chloride. Everything else really doesn't. And so when we add barium nitrate to the chloride, nothing's going to happen. No reaction. How about nitrate? When we add barium nitrate to nitrate, well, nothing's going to happen. And no reaction. So the only thing that the barium nitrate will react with will be sulfate, the bariums. Well, what likes nitrate? Well, all nitrates are soluble except sodium nitrate is soluble. All nitrates are soluble except no, calcium nitrate is soluble, barium nitrate is soluble, and strontium nitrate is soluble. All nitrates are soluble except they're all soluble. Yeah, there's no exceptions. And so how are we going to test for nitrate if nothing will precipitate out with nitrate? Well, if nothing precipitates out with nitrate, then we can't use a metathesis reaction. We're going to have to use something else. And that something else we're going to use is a redox reaction. And the redox reaction is going to go like this. So if we have nitrate, we're going to try to react that with iron 2 sulfate. And so what's happening here? What's happening here is nitrate is an oxidizing agent, and then iron 2 is a reducing agent. And so we're going to have a redox reaction where the nitrate will take electrons from iron 2. And so what's that reaction? That reaction shown here. Okay. And we'll just write it down. So 3 nitrates. Actually, not 3 nitrates, sorry. 3 iron 2s. Okay, 1 nitrate plus 3 iron 2s plus 4H plus yields 3 iron 3s plus NO gas plus 2H2O liquid. And so what we have here is we have a redox reaction. The redox reaction, we need nitrate and H+. Nitrate and H+, that's going to be our oxidizer. Iron 2, this is going to be our reducer. So I probably shouldn't have written it like this. And so the nitrate with the H+ is our oxidizer, the iron 2 is our reducer. This is our oxidizer in the reverse direction, iron 3, and our reducer in the reverse direction is nitrogen monoxide or nitric oxide. So we're going to generate a gas here. We're not generating a precipitate. And so this is a CCG. CCG stands for clear colorless gas. Can we test this gas with litmus? No. Yeah. How can we test this gas? Can we ignite this gas? Like hydrogen gas? No. Don't smell it. Don't smell this gas, otherwise we're going to have to.
Will you put it in lime water?
No. Lime water would have been good, but it's not going to work. And so we need some other way of detecting this gas, otherwise we can't detect the presence. And the way we're going to detect that gas is this. It turns out that if we add an excess of iron 2, you know what's in your blood? Is it iron 2 or iron 3? It turns out it's iron 2. And your blood likes to pick up what? Oxygen. But it would also pick up things like carbon monoxide, cyanide, and nitrogen monoxide. Yeah, so iron 2 actually likes to pick up NO gas. It's kind of like carbon monoxide in a way, or O2. And so it picks up the NO gas, and then it forms FeNO 2+. This is a CCG. This is light green. So this is light green solution. And so what we're going to do is we're going to go from light green solution and then the CCG, a clear colorless gas, to this. This is going to be a dark brown solution. Dark brown solution. And that dark brown solution is going to form with this. Okay, where did the acid come from? Here I have my nitrate, I have my FeSO4, but where am I getting the H plus from? You know where the H plus is coming from? This H plus is coming from concentrated H2SO4. Concentrated H2SO4 is, what's that called? Yeah, sulfuric acid. Concentrated sulfuric acid. Concentrated sulfuric acid causes third-degree burns, and so you got to watch out. We have the concentrated sulfuric acid in the auto dispenser on the right. Do you see that? Did I talk about the plunger? Yeah. Be careful with that. But the concentrated sulfuric acid is like syrup, and so this is like a little faucet here. We're going to dispense the concentrated sulfuric acid down the inside wall of the test tube. Do not hold the test tube with your fingers, because as the concentrated sulfuric acid hits that, it gets very hot. And it's like syrup, so what's going to happen is it's going to sink to the bottom of the test tube. And so down here we're going to have a CCS of concentrated sulfuric acid. Above here we're going to have a light green color. This is going to be a light green solution. That's going to contain nitrate and iron 2. And so what's missing? Well, in this light green solution, what's missing is the acid, the H+. All the acid went down to the bottom here. And we need the acid to mix with the nitrate and the iron 2, but we're not going to mix this. Do not mix this. You know why? Because we don't want too much reaction. In fact, we just want the reaction to occur here. You know, at the border or the interface here, we have the nitrate and the Fe2+ coming into contact with the H+, and then we get reaction. And so this is called the brown ring. Of course, if you mix it up, then good. And so what we're looking for is a brown solution. Brown solution. Not a precipitate, but a brown solution, liquids layer right at the interface there. All right, so some of the chemical hazards here are concentrated sulfuric acid causes severe burns. Sodium bismutate is a powerful oxidizer. Permanganate's a powerful oxidizer, so avoid contact with those. What else is hazardous? Silver nitrate is hazardous. What does silver nitrate do? Yeah, and at high concentrations, it causes burns and blisters, chemical blistering. Sodium hydroxide is a big eye hazard. Silver and lead and barium, heavy metals. So just try to avoid touching this stuff and avoid spills. If you do splash a little on you, wash it off for 15 minutes or so. If you spill like manganese hydroxide or manganese oxide, that's not that hazardous. So there's sodium bisulfate, no big deal. Sodium bisulfate, not that hazardous. All right, are there any questions? And so the report sheet's going to be two parts. The first part is just simply listing what cations you found and what anions you found. The second part is I want to see all the equations for all the reactions that occur in all the steps. Okay, the ones I just wrote.
Those ones they had 1, 2, 3, right in
No, all of them. Yeah, I did all of them. Your book doesn't have all of them. I did all of them. All right. If there are no other questions, the unknown is going to be individual. The known is group. So everybody's going to get their own unknown. Even though you get your own unknown, you could ask your neighbors for if you have questions, or you can ask me if you have questions.